So today is September 24th, and you're here for Economics 249. What you're looking at is some information about possible internships in information security, and it's open to all majors. So as I get information, I send them out to you. I might not have direct information, but I can point you in the right direction. So make sure you constantly check the announcements that I post on my lab. Um, and, it's difficult times, but start thinking about internships for 2021 summer because this is the time, they're advertising. Anyone has any questions for me? Yes, Red, go ahead.
Okay. Hi, Professor. I just wanted to ask you about the final exam. So I was going through the syllabus here. So it says exam 2 will be based on 5, 6, 7, and 10. And then our final exam on December 17th. So is the
Uh-huh.
final exam just based on chapter 10, 11, 12, or cumulative of all the chapters?
So the final exam will be based on what we do in exam 2 plus the 2 extra chapters.
Okay, got it.
Okay, so not what you did for exam 1.
Okay, all right, no worries. Thank you.
Okay, and everyone should have received my email that I sent out about the score for the last test that you took. So the score that you see on my lab is the score that I'm going to use now. It's fixed and corrected. If you never received an email from me, make sure you check the email address which you registered with on my lab because I send the emails out through my lab. Bipin, I see that you posted that the exam questions might have been difficult. They're very similar to the homework questions. So again, go back and read my email. And if you have particular issues with anything, email me directly and we can discuss it. Okay. Okay, so we're going to start with chapter 5. So today is a new chapter, and it's all about probability. So before we get into probability and all that stuff, I'm going to start with a small example. Let's say you are a marketing manager for an electronics company and you want to know something about your customers' intentions. Okay, you want to know something about your customers' intentions as a marketing manager for an electronics company. So the only way to find out is to send out a survey. So you send out a survey to your customers and you want to know specifically what their intentions are in purchasing a flat screen TV within the next year. Okay, how likely are they to purchase a flat screen TV within the next year? So you send out a survey and you collect some data and you get the survey back with all their responses. Okay, so now my question is, what are you going to do with all their responses, with all this data? Remember, you're the marketing manager. So how would this help you as a marketing manager once you get all their responses? What do you think? So you can use your microphone, you can type it in. My question is, once you collect all the responses back from the survey, what can you do as a marketing manager once you know their intentions in purchasing a flat screen TV within the next year? Shubham, you say analyze, okay. Harun, you say produce more or order more. So if you know they're very likely to purchase a flat screen TV, maybe you can increase your inventory, okay. Jennifer, you say you can compare the results, okay, you can compare to what how many were purchased last year, maybe, and now you know maybe it's more or less. So Priscilla, you say now that maybe you find out that it's less, they're less interested, less likely to purchase more. So now you need to do some kind of promotions as a marketing manager because you want to sell more. So you do some promotions. Karina says you use the data to create an ad campaign. I agree, right? So you can do all these things. What about the financial portion of it? So now you can almost predict what your sales would be, what your profit would be. You know how many units to order in inventory. You might know how many people to staff on the floor. So you can get so much information just by sending out a survey. So it all leads us back into this idea about predicting how likely an individual is in purchasing a flat screen TV. How likely? So that term, and I'm going to write it down here. How, actually, let's put it in quotations. How likely an event will occur, how likely means probability. So that's where this idea comes from. Now, predicting events is not very easy. So with random phenomena, we can't predict the individual outcomes. We can't precisely predict what their intentions are, but we hope to understand characteristics of their long-run behavior. If we understand characteristics of their behavior. So for any random phenomena, for any experiment, for any phenomenon that's happening, there's always an outcome. It generates an attempt or a trial or an outcome or an event. So all these terms really mean the same thing. For any experiment, which is a random phenomena, we always end up with some kind of outcome or event or attempt or trial. So what do I mean by a random phenomena, this experiment? Okay, so let's say the experiment is flipping a coin. Now, what are the different outcomes? I can get either heads or tails when I flip a coin. If I look at giving an exam, that could be my experiment. That's my random phenomena. So I give this experiment, this exam, and all the different outcomes can be anything from 0 to 100. And how long it takes to put something together, to assemble something. That could be my experiment. It could be anywhere from over 0 seconds. If my experiment is a course in a semester, then the outcomes can be anything from a grade of F to A+. So these are the different experiments and these are the different outcomes. If I want to calculate how likely a specific outcome is, if I want to calculate the probability of getting heads when I flip a coin, that means I'm calculating probability. So probabilities list the outcomes of a random experiment. Okay, so that's all it is. Don't make this really complex. This chapter is all calculating probabilities, but think of it like that. You have an experiment, you have outcomes, and now you want to calculate how likely an outcome will occur. So moving on with more definitions. The first one here is sample space. So a sample space is a collection of all possible outcomes in your experiment. So if my experiment or my random phenomena is to throw a die, now I can have 6 different outcomes in that die. So all the different 6 outcomes together is my sample space. So sample space equals 6, all possible outcomes. Another example, a deck of cards. So in a deck of cards, there are 52 different outcomes because there are 52 cards in a deck. So my sample space is equal to 52. Any questions about that? So it's all your total possible outcomes. Now, another definition is the word independence. We briefly looked at independence when we talked about categorical data, displaying and organizing our categorical data. Now, when we look at independence, it's more analytical. We're going to try to prove independence. So first, a definition. The outcome of one trial doesn't influence or change the outcome of another. So if I look at my experiment of throwing a die, whatever outcome I get is not going to affect the next time I throw my die, or it's not going to affect what I previously got as an outcome. So the outcomes are independent of each other. So the outcome of one trial doesn't influence or change the outcome of another. That's the meaning of independence. Couple more definitions, and you might have seen this when you took algebra or some math course prior to this course. So we have a simple event. A simple event is an outcome from a sample space with only one characteristic. So if my experiment is a deck of cards and you pick a card and that card happens to be a red card, then it has only one characteristic. So it's a simple event. A joint event involves two or more characteristics simultaneously. So again, deck of cards, if you pull out a card that is a red card and an ace card, now it has two characteristics happening at the same time. That would be considered a joint event. For this course, we're only going to look at two characteristics occurring simultaneously to be considered a joint event. It can get more complex where you look at more than two characteristics for a joint event. Okay, this is another definition that you need to know. Impossible event. So an impossible event is really a null event, something that cannot happen. It's impossible. So for example, if you pull out a card from a deck of cards, there's no way that you can get a club and a diamond on the same card. So that probability is zero. If the probability is zero, that means the event never occurs. It can never happen. It's a null event. It's an empty event. If the probability is 1, that means the event always occurs. It will always happen. So this is important to note here, this little notation. If I say the outcome or the event, I'm going to call it A. So the probability of event A, so this is what I'm talking about, this probability of event A, probability can be anything between 0 and 1. So if the probability of event A is 0, that means it will never happen. If the probability of event A occurring is 1, that means it always happens. Any questions for me? Okay. So now okay, let's go back and let me answer this question. Kevin, you says, what if you get an error on the card? So there's no such thing as error. Okay, it's just impossible event, null event, something that cannot happen. Next thing is to start with the definition of probability. So probability is a numerical measure of the likelihood that an event will occur. Okay, you don't memorize this, but you need to recognize this word. How likely an event will occur, the likelihood that an event will occur. If I can numerically calculate, numerically measure how likely an event will occur, that means I've calculated probability. That's all it is. Okay, so the likelihood that something will happen. Now, there are two types of probability. Well, when I say types, it's two methods of calculating probability. This is the first method. So I'll write that down here. model-based, or it's also called theoretical probability. So theoretical probability, now let's look at event A, can be computed like this. And you've probably seen this before, and you've probably done this before. The probability of event A is equal to, in the numerator, the number of outcomes in A, all the possible outcomes, the total number of outcomes for event A, divided by your sample space, divided by the total number of outcomes for that experiment. Okay, so this is the basic formula to calculate probability using this method, theoretical probability. So probability of A is equal to the number of outcomes in A divided by sample space. The second method you have seen before, and let's change, it's called empirical probability. And we've done this before. With empirical probability, we calculated relative frequency. So that's the method we used, relative frequency. And we did that with the chapter on quantitative data. So when I asked you to calculate relative frequency, I said take the value for frequency and divide it by the total. You were also calculating probability. That was empirical probability. But you were basically looking at the relative frequency of an event as the probability of an event. So same idea, but just a different method. Okay, something I wanted to mention, and I'll do it on a blank screen because I don't think the next slide is a blank screen. So let's see. Yeah, so I'm going to open a blank screen here. Okay, so basically I want to give you a simple understanding about the difference between statistics and probability. So it's not a perfect explanation, but at least you get the idea about the difference between statistics and probability. So we have circle here, circle here. This is my population, and this is my population. From my population, I randomly select a sample. Okay, so same thing for both. Population means everything under consideration. A sample means I randomly select a few items into my sample. Okay, let's start with statistics to explain the difference. Okay, so from my sample, the data that I have, I use some statistical method and come up with a result. The result is about my sample. That sample result is called a statistic. Okay, so I'll type that here, statistic. So the sample result is my statistic. So from that statistic, I can make an inference or a conclusion about my population. So I'll say that again. From my sample, I get a result. That sample result is called my statistic. Based on that sample result, based on that statistic, I can make an inference or a conclusion about the entire population. Now let's look at probability. Okay, so I'm going to start with an example. Let's say there's an assembly line of items, and I already know that 1% of all the items on that assembly line is defective. 1% is defective. I randomly select 5 items from that assembly line. That's my sample, right? So I have randomly selected 5 items. Now I want to know how likely will all 5 items be defective. So let me type that in here. So again, I randomly selected 5 items. I want to know how likely will all 5 items be defective. That's considered probability, right? How likely will an event occur? How likely will 2 items be defective? How likely will 0 items be defective? So what's the probability that all 5 are defective? So this is the basic difference between statistics and probability. Okay, so moving on, going back to our chapter 5. We were here. Okay, so now let's look at this example using this formula. So the example says, Pew Research reports that of 10,190 randomly generated working phone numbers, the initial results of the calls were as follows. Okay, so out of 10,190 randomly generated working phone numbers, Pew Research reported this. 311 calls had no answer. 61 calls were busy, and so on. 7,400 were actually contacted. Okay. Since the phone numbers were generated randomly, each was equally likely, and the probability of a contact is simply this. Now, I know you have the answer in front of you, but let's try to think about this a moment. Why would they say equally likely? Why is that information necessary? Each phone number was equally likely. What do you think? Yes, Judah? Judah, go ahead. Yeah. You said probability is the same. Brandon, you said there's no way of knowing which will occur. They have the same chance of occurring. So it's not about the probability. It's going back to that word independence. And Oscar, I think you're on the right track. So the word independence. So what did I mean by independence when I first introduced it to you today? I said that the outcome of one trial does not change the outcome of another trial. So I'm trying to mark it on this here. The outcome of one trial does not influence the outcome of another trial. So just because one phone number was contacted, it has nothing to do with the next phone number, and it will not affect the prior outcome. So they are independent of each other. They are equally likely, not related. Dongyan, yes. So there is no bias. Correct. Okay, so that's why we need to know that there is no connection with the phone calls. They are all equally likely and they're independent of each other. Okay, so now you're asked to find the probability of a contact. Okay, so that means you're asked to find this. Now I'm going to write the formula on the top first. I know the answers on the slide, but let's do it anyway. So the probability of contact, and I'm going to call that C. So find the probability of contact. According to the formula, the numerator says you need the total number of outcomes for C. So outcomes for C, okay, that's not good. Probability of C is equal to total outcomes for contacted numbers is 7,400 divided by the total. So according to the slide, the total is 10,190. Okay, this is not working, but the total is 10,190. So that's where we get 7,400 divided by 10,190 as the probability for contacted numbers. So the numerator has the contacted numbers outcome divided by the sample space. When you're doing your homework and you're asked a question to calculate probability like this, read the question carefully, because if it asks for 4 decimal places, then make sure you have 4 decimal places. If you ask for 2, then you would put 0.73. If you ask for a percentage without decimal places, you would put 73%. So probability can be written as a percent or as a decimal. Okay, questions for me? Now, if I asked you to calculate the probability of no answer, that means, let's do another column here that says, let's do it this way. If you have a third column here that asks for probability, now this value came out to be 0.73 for contacted numbers. So this would be 311 divided by 10,000. So I'll write that down. 311 divided by 10,190, and you would get that answer. So if I go to my thanks. Okay, I'll put that down. 0.0305. Okay. We can see that there's some similarities going on here. It's telling me that the probabilities for every outcome is between 0 and 1. And if I actually add up all the probabilities that I get as a total, I should get 1. Or if I'm looking at a percentage, that would be 100%. So that brings us to the next slide. Okay, which talks about the rules of probability. So rule number 1, okay, it's jumping. Let's start with rule number 1. Rule number 1 says that if the probability of an event is 0, then that event can't occur. If the probability is 1, then the event always occurs. So this is really the rule. When you calculate probability, it should always be between 0 and 1. Okay, your value will always be between 0 and 1. It can be 0, it can be 1. The second rule is that when you add up all the probabilities, all the possible outcomes in your experiment, the total must be equal to 1. Or if it's a percentage, then the total will be 100%. These two terms are important. Oh, it's not going again. Okay. Mutually exclusive and collectively exhaustive. So the sum of the probabilities of all mutually exclusive and collectively exhaustive events is 1. So first I'll give you the definitions. Collectively exhaustive means all outcomes are included. All outcomes are included, collectively exhaustive. Mutually exclusive means 2 outcomes cannot occur at the same time. Mutually exclusive means two outcomes cannot occur at the same time. So let's go back to the previous example with the phone calls and apply these definitions. Okay, so here we are.
Wait, what you said for collectively exhaustive?
Okay, so collectively exhaustive means all outcomes are included. What do I mean by that? All outcomes are included. They said that out of the 10,000 some odd phone numbers, these are all the outcomes. Either there's no answer when they call the phone, either the line is busy, they get the answering machine, and so on. Now, is there any other outcome that is not listed here? Probably not. I think they've included every possible outcome here. So if they have included every possible outcome in this experiment, then this list is collectively exhaustive. Okay, so it's collectively exhaustive. All outcomes are included. Now, what does it mean by mutually exclusive? So when one of the researchers has a phone number that they call, the result can only be one of these. You cannot have the answering machine and have the line busy at the same time. That's not going to happen. So that means all these outcomes are mutually exclusive. They cannot happen at the same time. Okay, so that's what that definition means. It cannot occur at the same time. So if I take the sum of all these probabilities, now that means the outcomes are mutually exclusive and I have included every possible outcome. So if I take the sum, that total must be equal to 1. So that's what the second rule is saying. The sum of the probabilities of all mutually exclusive and collectively exhaustive events is 1. Okay, let's move on. Complement of event is rule number 3. So instead of memorizing this slide and, don't make it complicated, complement means opposite, the opposite of an event. So if I'm talking about event A, then complement of event A would be the opposite of whatever is in A. All events not in A would be the complement. Complement of an event is denoted like this, A complement with the A superscript C, or it's written like this, A with an apostrophe, that's also A complement. So let's look at this example. If event A is Queen of Diamonds, then complement of A would be all cards in the deck that are not Queen of Diamonds. So the probability of event A would be everything else, the sum of all, 1, minus that complement, minus the opposite. That would be the probability of that event. Again, don't memorize this. It's just very simple. Think of it as the opposite. And we'll do a few exercises so you can get comfortable. So now let's start with, okay, this is our first example. It's about Lee's Lights. So Lee's Lights sells lighting fixtures. Lee records the behavior of 1,000 customers entering the store during 1 week. Of those, 300 make purchases. What is the probability that a customer doesn't make a purchase? Okay, now I know that you see the answer in front of you, but again, I'm going to open a blank screen so that I can write and explain how we can do this by applying the formula that we just talked about. Okay, so we have, and I'll type it so it's neater. We have outcomes, we have customers, And then we have probability. Okay. So we have this store called Lee's Lights. And what Lee did is he recorded the behavior of 1,000 customers entering the store during 1 week. So we know that the total number of customers is 1,000. Okay. And now we need to state what the outcomes are. So when a customer enters a store, either the customer, let me write it down here, could make a purchase. What else can the customer do? Either the customer makes a purchase or the customer does not make a purchase. Okay, so those are the two outcomes. Just to make it simple, we're only starting off with two possible outcomes. Okay, and we're also told that the customers out of the 1,000 customers, 300 make a purchase. Okay, and now if I want to find the probability of what's the probability of a customer making a purchase? Now, using my formula from before, I would take the total number of purchases and divide it by the 1,000. And yes, Priscilla, that is 30% or 0.30. Yes. Now, the question is asking you, what is the probability that a customer doesn't make a purchase? Now, you can do this in many different ways. I'm just going to stick to this. So that's right. If we did 1,000 customers minus the 300, so we have 700 customers who don't make a purchase. Or if you wanted to find the probability, you could have done 700 divided by 1,000, and that's 0.70. That's right. Is there another method that I could have got 0.70 rather than what I just did? Rather than doing 700 divided by 1,000, Matthew, yes, 1 minus 0.30, because I know according to my second probability rule, the sum of all probabilities in an experiment must be equal to 1.00. Total probability must be equal to 1. So that means I can also find 1 minus 0.30 would give me 0.70. So yeah, so that's how you would answer this question. What is the probability that a customer doesn't make a purchase? What's the probability of the complement of purchase? What's the probability of the complement of purchase? Judah, that's right. Arzu, that's right. It's 0.70. Remember, complement just means the opposite of purchase. Yeah. Does this satisfy rule number 1? What we just did, does it satisfy rule number 1? So Urmila or Ying, do you want to explain why it satisfies rule number 1?
Because it's between 0 and 1.
Yes. So it's because each of these values are between 0 and 1. Yeah, so it satisfies rule number 1. Okay, any questions about this? Very simple, right? Not difficult. So let's move on, going back to chapter 5 slides. Okay. So this is where we were at. Moving on to the next slide. So the next slide is about the next rule, number 4, which is the multiplication rule. So now it says for two independent events, A and B, the probability that both A and B occur is the product of the probabilities of the two events. So a couple of things happening here. First, this word independent. So again, you need to understand the meaning of independent. So the outcome of one does not influence the outcome of another. So the outcome of event A does not influence the outcome of event B. So if event A and B are independent, then I can apply the multiplication rule, which says that what's the probability that both A and B occur? So this word and in math, okay, basically means multiplication. It's a product. Okay, so when you see the word and, it means product. Probability that A and B occur means take the probability of A times take the probability of B. So let's move on to our Lee's lights example. Now here it says that if we can assume that customers behave independently, okay, so let's think about that. Customers behave independently. When one customer comes into the store, the outcome does not influence or affect the outcome of another customer. So their outcomes are independent of each other. What is the probability that the next two customers entering Lee's lights both make a purchase? So customer A makes a purchase and customer B makes a purchase. What's the probability that they both make a purchase? So the word both is in the question, which means A and B, which means you're going to use the multiplication rule. So that means you already know from the continuing with this example that we calculated the probability of purchase as 0.30. So that means you take 0.30 and 0.30, so 0.30 times 0.30, and that probability is 9%. The probability that they both make a purchase is 9%. Any questions for me?
Can that be the probability for non-purchase also?
No. So this is only for purchase. If I had to calculate the probability that both don't make a purchase, who wants to give us that answer? The probability that they both don't make a purchase.
That is 0.7. What I mean is if you can also calculate the non-purchase like this.
Yes, so Judah just gave the answer. Yes, so Kathleen, you're right. 0.7 times 0.7. So you're right. Yes. You could do the same thing. Yeah. So this is just asking, find the probability that they both make a purchase. Okay, so you can do the same thing. Yes. And moving on to the next rule. The next rule is the addition rule. So this would be rule number 5. Two events are disjoint or mutually exclusive if they have no outcomes in common. Okay, so disjoint means the same thing as mutually exclusive. And I gave you the definition before for mutually exclusive. I said that two outcomes cannot occur at the same time. They cannot happen at the same time. They are mutually exclusive. So if the two events are mutually exclusive, cannot happen at the same time, then we can use the addition rule. So the addition rule says that the probability either A or B occurs. Either A or B. So again, in math, when you see the word or, that means you add. Probability that A happens or B happens. They cannot happen at the same time because they're mutually exclusive, okay, which also means disjoint. Okay, so let's apply that to our example about Lee's lights. Okay, so here it says some customers prefer to see the merchandise but then make their purchase online. Lee determines that there's an 9% chance of a customer making a purchase in this way. We know that about 30% of customers make purchases when they enter the store. What is the probability that a customer who enters the store makes no purchase at all? Okay, a lot going on here. I'm going to open my blank screen so I can explain. Okay, so let's start with outcomes, and then we had customer, and then we had probability. Oh, that's too high. Okay. So we were told that when a customer enters the store, the customer can make a purchase. The customer can make no purchase. Anything else now? We were told that the customer can purchase online. So now here's a new outcome. Okay. And we're told that, reading the question, Lee determines that there's a 9% chance of a customer making a purchase online. So we're given this online probability of 9%. We're already given that. And we know that from before, this is the same, the 30%. Okay. Now, a lot of things happening here. Let's write this down. This total must be equal to 100%. Okay. My first question is this collectively exhaustive? So what do you think? Is it collectively exhaustive? Are all outcomes included? So yes, all outcomes are included. There doesn't seem to be any other outcome when a customer enters the store. Either they make a purchase, they don't make a purchase, or the option is to go online and purchase. Okay, so it seems to be collectively exhaustive at this point. Now, the reason we're doing this is to apply the addition rule. So what I'm going to do is type the addition rule here. A plus the probability of B. Okay, so this is the addition rule, which says that the events are mutually exclusive. So we're told that you can't do all these three outcomes at the same time. You have to be able to either purchase or not purchase or purchase online. Okay, so we're assuming all these outcomes are mutually exclusive. So now you're asked in the question, what is the probability that a customer who enters the store makes no purchase at all? But before we do that, let's apply the addition rule. So what's the probability that a customer makes a purchase or purchases online? Okay, so that's what I'm going to type here. The probability that a customer makes a purchase or online is equal to total probability of purchase. Yep, 30% plus the 9%. Exactly. So that's 39%. So that's applying my addition rule. But that didn't answer the question, because the question asked, what is the probability that a customer enters the store, makes no purchase at all? So that's when I go in here, and now I can calculate the 100 minus 39% is equal to 61%. So any questions? This is showing you how we applied the addition rule and then answered the question. Okay, so I'm going to move back to our slides. Questions for me? No? Okay, so going back to last slide. Where are we? So that's what you're looking at, the 0.61%. Moving on to the next slide is rule number 6. So rule number 6 is about your general addition rule. General addition rule. So it's the same thing that we just saw, but now we're saying that what if you have events that can happen at the same time, that can be, that are not mutually exclusive. The events are not mutually exclusive. So then you can apply the general addition rule. So this is the same formula, but now you have this little addition at the end minus the probability of A and B. So you're asked, what is the probability of A occurring or B occurring? And they could happen at the same time. So that formula says take the total probability of A plus total probability of B minus whatever they have in common minus the probability of A and B. Okay, so let's go back to our Lee's lights example. And this last part says, Lee notices that when two customers enter the store together, their purchases are not disjoint. They are not mutually exclusive, which means they can happen at the same time. In fact, there's a 20% probability they'll both make a purchase. Now, this information has to be given to you. Probability that they both make a purchase. When two customers enter the store together, what is the probability that at least one of them will make a purchase? Okay, this is your clue to use the general addition rule. At least one. So whenever you see at least one, that means you're going to do the probability of A plus probability of B minus probability of A and B. At least one makes a purchase. So you know from before the probability that A makes a purchase is 0.30 plus the probability that B makes a purchase is 0.30 minus, now you're told that there's a 20% probability that they both make a purchase, so minus the 0.20, and that's how you get 0.40. And you've applied the general addition rule. Any questions? So with probabilities, the best way is to just practice a few problems and you'll get the hang of it. Don't read too much into it. It's not really difficult, but it's kind of like logic, right? So Priscilla, you said, how do you get the 20%? It's given. Diana answered your question. It's given in the question. At this point, there's no way for you to know how to get the 20%. Let's do this next problem together. And I'm waiting for it to load. Okay, so the answer choices that you see at the bottom, they're all mixed up. They're not in any particular order. So that means I'm going to be doing a poll question for this. Okay, but we'll work on it together. So the question says, you and a friend get your cars inspected. Okay, so you take your cars to get inspected. The event of your car's passing inspection is independent of your friend's car. Okay, that's important to know. That's telling you that no matter what the outcome of your car, it has nothing to do with your friend's car and vice versa. Okay, so when you take your car to be inspected, either it passes inspection or it fails inspection. So there's only two options, right? Either passing inspection or failing inspection. Now you're told if 75% of cars pass inspection, then what is the probability that, and you have to answer all these 5 questions. So I'm going to go to the next blank screen and we're going to start this together and you're going to give me some answers. So the first question is, what is the probability that your car passes inspection? And I'm putting it as a poll question here. Till that loads, let me type it up here. So we have outcomes, and then we have probability. So we have 2 different outcomes. I can see you already put that in. Either you can pass inspection, or if you don't pass, then you fail inspection. And we're told that the probability of passing inspection is 75% or 0.75. Okay, so that's all you have for now. And the first question is, waiting for this to load so I can start the poll. Okay, 0.5 to 5. Second choice is 0.75, 0.9375. Okay, so first question says, what's the probability that your car passes inspection? Okay, you have a few more seconds. Stopping the responses now. So most of you said 0.75, and 0.75 is correct. Okay. So the second question says, what's the probability that your car doesn't pass inspection? And let's see. So what's the probability that your car doesn't pass inspection? And according to the answer choices that I've given, is it answer choice B? I can't really see what answer choice B is, but
What's the question again?
the question asks, what is the probability that your car doesn't pass inspection? So is it answer choice B? And I don't see what answer choice B is because I can't.
It's 0.75.
Okay, so answer choice B says that it's 0.75. So yes or no, is it 0.75 or is it not 0.75? Okay, and I'm stopping responses here. So you're telling me the probability that your car doesn't pass inspection. Okay. So most of you said no, it is not answer choice B because that would be incorrect, right? So it's not this. It should be, this total is 1. So 1 minus 0.75, yeah, is E, correct. So the answer choice is 0.25. Okay. Next question is, what is the probability that both cars pass inspection? So this, I'm going to type it up. Both cars pass inspection. So the probability that you pass, so I'll say you pass inspection and your friend passes inspection, and means multiplication. So you and your friend would be 0.75 times 0.75, and what do you get? So the probability that both cars pass inspection is equal to, yes, answer choice A. That's right. Okay, let's do the next one. Next question says, what is the probability that at least one of the two cars pass inspection? At least one. So that means the first car or the second car. I mean, your car or your friend's car, at least one. So again, there's that word at least. So the probability that at least one means you or your friend pass inspection is equal to you passing inspection is 0.75 plus your friend passing inspection is 0.75 minus what? Remember, this is the general addition rule because it's possible that both can pass inspection. It's possible that they are not mutually exclusive. So minus something. Minus, correct. Yes, Judah, you're right. Minus the 0.5625, and that is equal to, so Ying, you're wrong with that. Yes, the answer is C. Okay. So this is probability that at least one of two cars passes inspection. Okay, and then the final question is asking you to find the probability that neither car passes inspection.
Wait,
Neither.
what do you minus for that one?
So it's that general addition rule. Probability of A plus probability of B minus the probability of A and B. So this is my probability of passing minus the probability of not of my friend passing. Sorry, let me start that again. Probability of me passing plus probability of my friend's car passing minus this amount which I got from here. Oh, it's all messed up here, but I got it from before. Friend and you passing, the and 0.75 times 0.75. So that's the 0.5625. Does that answer your question?
Yes, thank you.
Okay, and then the final thing you asked is to find the probability that neither car passing inspection. So if you don't pass, that means you fail and your friend's car fails. You and your friend fail inspection. So
And
that would,
sorry to cut you off again.
uh-huh.
Do you mean equal D? That was D. That question was D,
The
right?
one before, it was the one in blue. The
Yeah.
answer is C.
Oh, okay. The
Oh,
answer is,
wait.
but
Hold on. Did I make a mistake? No, the
yeah.
answer is C.
Oh, okay. Thank you.
Yeah. So the one in blue, the answer is C.
All right.
And this one, so you and your friend fail inspection is answer choice D, correcting. Yeah. There's a different way of doing the answer for D. Does anyone recognize a different way of doing this? And if you don't recognize it, it's fine. I'll leave it as it is. If you don't recognize any other way, but if you do, it's fine as well, because I want to make sure that you are comfortable with doing this. Yes, Armila, that's right. Yeah. Dongyan, yeah. So again, the best way to do this is to practice. There are homework problems to do this. There's extra study plan problems when you're practicing for the next test. But I'm going to stop here for today. It's a lot of information. Your homework is not due this Sunday. It's due the following Sunday. We do not have class next week on Tuesday because it's Monday schedule. Okay, so we will not meet. You have Monday schedule classes. All right, so I'm stopping the recording.